Segment 53, Big Bang Cosmology. In trying to understand how the universe got to be the way it is now, we have to look at the various epochs in the universe and understand the physics of what's going on in those epochs, and then test models with the places where we can make observations. So we believe that the universe started out as infinitely small and infinitely hot, and spontaneously started to expand, and in a tiny fraction of a second expanded at an enormous rate in a period that we call the inflationary period. This period turns out to be necessary to explain some of the key features of our current universe. The universe that we observe actually begins about 380,000 years after the Big Bang, when the universe becomes transparent. In that earlier epoch, where all of the gas was ionized, the universe was opaque to electromagnetic radiation, and we can't see through into that era. We look at this opaque wall, trying to infer what happened before that time, and then can follow the evolution after that to the present day, 13.7 billion years after the Big Bang, where we have the universe of galaxies and stars that we know today. So here are the big picture questions about the universe. How did the universe get its present matter distribution? Why do we have galaxies and voids and walls of galaxies and things of that sort? What will be the ultimate fate of the universe? Where will the universe be billions of years from now? How did the universe evolve to produce the solar system? That is, this provides kind of a segue from our current study of the universe as a whole to the study of solar systems, which we'll be talking about next week. So we need to mix the answers to these questions and try to understand how all of this came about. So here are some of the puzzles about how the universe began. How did the expansion get started? What is the expansion rate history? And why do we have the amount of hydrogen and helium we have now? The prediction of an early compact hot phase is pretty obvious once you see the observation that the universe is expanding. As you run the clock backwards and move back in time, the material was closer together. Obviously, the densities were higher. And as you squeeze down the size of the universe, the characteristic scale lengths get shorter and shorter, so the wavelengths of the photons get shorter and shorter, and the higher frequency, shorter wavelength photons imply higher energies and higher temperatures. So the earlier universe was denser, more compact, smaller in total size, and much hotter. But why should this lead to black body radiation in the microwaves? So let's try to understand that as we go through things. Let me just also mention this principle that I mentioned the other day, the cosmological principle of homogeneity and isotropy. That is, that the universe is pretty much the same everywhere and pretty much the same in every direction that we look if you go to a large enough scale. And this principle is just saying we're not special. We're not at some place special in the universe. And any kind of model that violates these principles is not likely to be the model of the universe as we see it. So here's now a cartoon version of what we've been talking about, looking at the era from the Big Bang to the present and trying to understand how we get here. And so we're going to talk about various observations that move us along this route. It starts with an observation that was made now about 50 years ago with a telescope in Holmdel, New Jersey. This is a radio telescope run by actually the telephone company, AT&T, Bell Labs, which was a research facility for the telephone company. And the antenna you see in the background is similar to the antennas that were used at the time for relaying microwave signals from tower to tower across the country, which was how telephone transmission was done at that time. And these two scientists, Arno Penzias and Robert Wilson, were looking for extraneous noise, extra emission that might affect the telephone signals. And they found that everywhere they looked, there was some residual signal that they couldn't account for in their apparatus. And at one point, they even thought it might be due to radiation from the pigeon droppings inside the antenna. So these guys got the Nobel Prize partly for cleaning the pigeon droppings out of the antenna that you see in the background. What they discovered was this ubiquitous radiation with a characteristic temperature of a 3 degree black body. So radiation coming from everywhere that was fairly faint. So why does this have a connection to the Big Bang? Well, the idea is that if the universe was hot and ionized, that scattering off of the free electrons in the gas would make the universe opaque. But as the universe expanded and it cooled, it reached a temperature where the protons and electrons didn't want to stay separate from each other. And the hydrogen then recombined. The hydrogen went from an ionized state to a neutral state, at which point it became transparent. So when you look out in space, back in time, until you see this. You're looking back to a time only a few 100,000 years after the Big Bang where the universe was ionized. And you're seeing this ionized surface that was emitting at a black body temperature of about 3,000 degrees. But because the universe is expanding, the photons that come from this surface of last scattering have been expanding as they travel to us until at the present time they're about 1,000 times longer wavelength than they were originally. And so the black body we see, instead of being 3,000 degrees, looks to be about 3 degrees. It's as if you were, when you look on a cloudy day at the sky, you see the bottoms of clouds. The light is coming from the sun, but it's scattering through these clouds, and that surface you see is the surface of last scattering, where the atmosphere goes from being opaque and scattering light to being transparent. And so you look up to see just that boundary. Same thing's true with this early universe. We're looking back to that opaque surface. This was demonstrated beautifully by observations with a satellite called COBE, the Cosmic Microwave Background Explorer. And the observations showed that the emission from this surface of last scattering were almost a perfect black body, which is just what the theory of the early universe had predicted. And so what you're seeing here is a comparison of a theoretical black body spectrum with the observations, but they're so close together that the blue line is showing you both at the same time. And this resulted in a Nobel Prize for John Mather, a scientist that works for NASA, in 2006. Also part of that prize went to another experiment on the COBE satellite that showed the distribution of the radiation. If the radiation, if the surface is moving slightly, or if you're moving with respect to the surface by a small amount, it will look hotter as you move towards it, and a little cooler as you look away from it. And the dominant variation on the sky is a dipole, meaning that something is in motion. And in fact, it's the galaxy and the Earth moving around the sun, and the sun moving around the center of the galaxy, that are all in motion. And these combined motions lead to a pattern on the sky that you see here, where one side is slightly hotter and one side is slightly cooler. When you take this pattern out, so that's the pattern you're seeing in the top frame, what you see is what's in the middle frame here. And that middle frame is dominated by a stripe across the sky that's due to emission from the Milky Way galaxy. So that's just local emission in the galaxy, a foreground to this cosmic microwave background. By looking at different wavelengths, since that emission has not a blackbody spectrum, but quite a different spectrum, we can subtract that emission out, and then you're left with the bottom picture showing the distribution of flux from the cosmic microwave background. And this experiment has been repeated several times since it's such a fundamental experiment. And the most modern version of it has just been completed by a satellite called the Planck satellite, a European satellite, showing in much more detail the variations on the background. But the peak-to-peak variations in this plot are less than 1 part in 10 to the 4. It's less than 1 part in 10,000. So the variations in the temperature from a 2.78 degree black body are tiny, only less than a thousandth of a degree across the surface. So they're very precisely measuring these very, very slight variations in the temperature as we look over the whole sky at this background. That very smooth universe, where it varies by less than 1 part in 10,000, has to grow to the current epoch. This is now the Sloan survey that we've looked at before, to a very, very lumpy universe with these vast voids and these walls of galaxies everywhere. So how do you get from this very, very smooth universe a few 100,000 years after the Big Bang to 13 billion years later, having this very, very structured universe that we see now? And the answer is you need a lot of matter interacting under the force of gravity. Most of that matter is dark matter. And people have done computer simulations starting with the smooth universe after a few 100,000 years and evolving it over time to see under the force of gravity to see how it would work. And this next plot is a simulation, a computer simulation of that kind of evolution of cool dark matter starting at the time of a few 100,000 years after the Big Bang. And you see a very strong resemblance between this ropey structure with big voids in it in the simulation and what you saw in the actual observations from the Sloan survey. So we think we have a pretty good idea of how this comes about now, how the evolution is coming about, at least in the structure of the universe over time. Another approach to studying evolution of the universe is to look at the Hubble law, at the redshift versus distance, out to very large distances, with the idea of testing various possible models for how the universe evolved. And it was this approach to studying cosmology that led to the amazing discovery of the dark energy. So here's a plot modeling the distance versus velocity, here with somewhat different units, redshift on the x-axis and a proxy for distance on the y-axis. And these observations showed a small deviation from what we would expect, but in a completely unexpected direction. That is, that the universe, instead of slowing down because of the mutual interaction of gravity, was actually accelerating, speeding up with time. This is the origin of the discovery of dark energy, which led last year to Nobel Prizes for the people who did this work with the supernovae originally. It's a completely unexpected phenomenon that changes utterly our picture of the universe. And this plot here is showing what we expect to happen over time with the universe under different conditions, depending upon how much matter and how much dark energy there is. And the current favored models, the red model at the top, where the universe initially slowed down because of the mutual interaction of gravity, but then gradually, as the influence of dark energy became larger and larger, it went from slowing down to speeding up, and we're now at this kind of saddle point where the universe is going from being dominated by dark matter to being dominated by dark energy, and we expect in the future the acceleration of the universe to pick up and the galaxies to fly apart faster and faster. You'll also notice that the time back to the origin of the universe depends, even though we measure a Hubble time of 13.7 billion years, depends on which of these cosmological models is in fact correct. One of the ways we discover what happened before the cosmic microwave background became transparent is by looking at the distribution of the fluctuations. And by studying how this distribution compares to models of the universe, we can understand things about the origin of the structure and about what was going on in the physics of the universe before that time. And we do that by looking at what spatial scales the power is distributed on, and scientists use that to compare to models to try to understand what's going on. So here is an example of some of the models with different parameters and how those fluctuations as a function of size scale look, and that's what gets used to try to understand things. Here's the actual observations compared to a best fit model based on observations like the Planck satellite observations that I showed you a little while ago. So this was an older slide showing history of the universe and different epochs, starting from the Big Bang, going through this inflationary period as the various fundamental forces of the universe separated from each other, and this acceleration went on very quickly. And then we're dominated by very energetic particles and by radiation for a period of time. And then the matter dominates the universe as gravity starts to slow things down. Of course, what's missing from this slide is the dark energy, because this slide's older than the discovery of dark energy, which is now what's dominating the history of the universe. The other aspect of this we need to look at is the formation of the elements. The universe started out just as this soup of photons, and as the universe expanded and cooled off, particles were created. And initially these particles were created and then destroyed, and the particles and the antiparticles would get created and then destroyed. And then eventually, as the universe cooled, we had a slight overabundance of normal matter, and we formed hydrogen. Some of this hydrogen could then interact with itself and create helium atoms and deuterium. But by the time a significant amount of helium had been created, the universe had cooled too much and become less dense enough that it wasn't possible to create the heavier elements that need very high densities, that the kind that we only find in the cores of stars, to be created. So the initial universe was almost entirely hydrogen and helium, and all the heavier elements had to be created later inside of stars. The relative amount of hydrogen and helium tells you something about the history of the early universe, about how density unfolded as the temperature decreased. So when we want to talk about the history of abundances of the elements that we need to make planets and people and things like that, that's really a history of what happened after the Big Bang, a history of what happened in the universe that we have today.